students online, if you encounter any difficulty in listening to my voice, please. I think the quickest way is to turn on your mic and let me know that. And if you put some message in the chat window, probably it is a little bit difficult for me to catch that. And some of my Elizabeth did a very good job to help me catch some messages sent by the online students. So online students, I encourage you to, if you encounter any technical issues or you see any issues on my side, just turn on your mic and let me know that. I think that's a quicker way to deal with the technical issues here. So last time we talked about the window. As you can see, green probably is better too. And today we will also talk about larger dynamic structure level. So one of them is the blast level. Blast level today. Sorry, the touch screen does not work. That is much worse than my surface. So blast level. So the reason why we need to design is the structure, you need to consider blast level, especially after 911. 911, the new concerns for civilian structures. New concern for civilian structures. Because before 911, the cases only the military structures are designed for blast load, but after 911, we know that some civilian structures is also target of some terrorism. So, especially in New York City, after 911, New York City requires most of the skyscrapers designed for blast load. So we know that the blast load bunkers and from TNT explosives. Then instantaneous release of energy. And like a short wave, Definitely, it's a dynamic load. So, for example, as you can see here, if we show the time history of the blast load, this is the time, and this is the pressure.
Dr. Yang, online we're just seeing your Blackboard page still.
So the team, what? So you
Blackboard page.
are you still on my Blackboard page?
Yeah.
How about now?
Okay, yeah, I see it now.
Okay. Summary then. Yeah. Okay. So so typically when we consider the blast load, we usually concerns about after the explosion of the TNT, there will be some pressure up to the exterior surfaces of your structures. So, and the pressure varies with time, right? So typically, you will see some variation of pressure like this. So that's the typical blast load when you design structures here. So if you look at the shape of the pressure induced by the blast load, we will have some positive pressure as well as some negative pressure. So question for you is, what does positive pressure mean and what does negative pressure mean over here? Why? Yes, Hunter? So if we talk about positive pressure, that means the pressure is perpendicular to the surface of the building and push the building inside. And then if we have the negative pressure, that means yes, it's more like a vacuum, so the surface of the building is pulled by the pressure outside. Outwards and inwards, so there are two. So that's why when you design for blast load, you have to consider both of those. So now let me give you some videos on the typical blast loading here.
There are inherent dangers in the oil and gas industry.
Online students, can you guys see the YouTube video on your screen now?
Yeah, I can see it.
Okay.
Yeah.
You do what you can to hire the best and brightest. You put safety protocols in place, and you create programs to train your team on safe practices. Despite that, incidents can still happen. Finding a trusted partner can mean the difference between life and death. At RedGuard, we manufacture modular blast-resistant buildings. Our temporary and permanent modular buildings set the bar for blast protection. We believe our customers deserve to know how we determine that our spaces are safe and trusted. It starts with engineering and structural design, but it doesn't end there. Putting our designs to the test is part of the process. We call it being tested for life. To follow up a successful blast test we completed in 2007, we set out to prove what our engineering models told us, that steel blast-resistant buildings were the best choice for safety. In 2020, we tested our structures in a remote area with hundreds of acres available, giving us plenty of space to create a massive explosion to emulate a large-scale blast on a hazardous worksite. To demonstrate the safety of our designs, we used 2 independent teams of expert engineers. In that test, we created what we believe is the largest scale blast test on a range of buildings. The first independent firm, an engineering firm specializing in analyzing and testing a variety of hazards, staged the explosion and provided a post-test assessment. The second independent firm advised us in testing, observed the explosion, and advised on building design. We know that when it comes to explosions, there are many factors at play, but distance is the big equalizer. We placed buildings at just 173 and 193 feet from what would be the explosion's epicenter. We put a crash test dummy in each building to detect if humans would have been injured in the explosion. The explosion employed a charge of 6,000 pounds of ammonium nitrate and fuel oil that created a 9.9 psi free field pressure blast at 24 milliseconds, simulating the damage of a very large explosion that could occur in a high hazardous process area. Through 34 channels of data, plus data from the crash test dummy, independent engineers concluded that our structures in both anchored and unanchored buildings had low responses. Low response means the buildings were largely undamaged. Each of them could still be occupied and in use after a blast of this kind. And other than possible ear injury, any human inside would have walked away from this large explosion. We're sometimes asked, what makes the difference? Time and again, we come back to our solid design and steel components. RedGuard buildings are built to withstand hazards using multiple redundancies to ensure safety. Each building has tightly spaced vertical stiffeners in the walls and horizontal stiffeners in the roof. In a redundant system like this, multiple components of the building would have to fail to constitute a complete building failure. Another component of safety is the dynamic load transfer, or flex, observed in RedGuard buildings. Flex is used to describe the way a steel wall quickly bends and retracts during a blast event. It can happen so fast that it's barely visible to the naked eye. But when steel flexes, it's actually absorbing the blast wave rather than reflecting it. Other buildings that use more brittle materials, think concrete, allow the blast wave to impact the walls, but the stress of the blast is then focused on the building's connections or joints. Other companies may consider their design unmatched, staying static as the industry changes around them. At RedGuard, we're always growing our design and capabilities, adding value for our customers, and advancing the industry with new design techniques, like our anchoring and foundation designs. We take risks in testing so that our customers don't have to take real-world risks. We'd never sell a building that didn't pass the test. Mathematical models can predict how objects and structures will respond to a blast event, but testing is the key. When all is said and done, occupants of our buildings have peace of mind, knowing that they will go home safe at the end of the day.
Yang. So for Oklahoma City, Timothy McVeigh put the bomb in the building, and for 9/11, planes attacked the actual building. Like, these are things outside, not
Okay, very good question.
inside.
Very good question. I would say,
Were you just screwed at that point?
So very good question. So most of the terrorist attack, would they were well planned, and for regular design, those type of load is very difficult to predict. I would say the possibility of you will have the next terrorist attack for a very important building or structure can be highly reduced by the new security, homeland security procedure. So I think when you do design, you do want to consider the possibility of the node exceeding the your design over here. So that's why nowadays, if you look at the ASC, so it's different from the ASC 7, the minimum design for building or other structures. There is another ASC document specifying how to design structures for blast loading due to the gas or oil explosion there. So that's why most of the design based on that. The case that you said, yeah, it's under the consideration of the engineers, but it's not only the job of engineers. It's combined work, engineers and policy makers. So when we consider blast load, typically we consider the explosive, the explosion occurs outside of the building. For example, some very critical buildings may have some concrete blocks to protect the approaching of some potential terrorist attack.
Yeah, those kind of showed up like after 9/11
Yes.
around a lot of buildings in New York.
Yes.
And you couldn't like drive your car into the building.
Yes, yes. So that's the new policy here. So if you want to design a building that is able to resist the explosion from inside, or that would be very difficult. You are not designing a building, you may have to design a bunker, nuclear attack. So that's a different story here. Very, very good point. Very good point. Yes, Tony.
But with that comes where you design to prevent cost is going to go.
Yes. Yeah.
And difference in price.
Yeah. Yes. Probably the owner would invest that money in the security or staff so that the building can be better protected. Right? Invest money in the military, so or in intelligence agencies so that they can be protected. That kind of it's not only the engineer. Any questions from the students online? Okay, so for engineers, the most common work is design the structures against the explosion in the oil and gas industry. Right? That the frequency of that kind of work is another kind of hazard that is more, it's much higher than terrorist attack, especially after 9/11. So how many terrorist attacks have you heard about recently? The most recent news about the terrorist attack looks like Nashville last year. The explosion and of a van in downtown of Nashville, but that kind of attack induces explosion outside of buildings too. So anyway, if you are interested in and how to design the building on the blast node, ASC does have some specifications for this. For example, on how to calculate the blast load and how to model your buildings. So the way you model buildings on the blast load is a little bit different from how you simulate in the building under other types of loads there. And, And since the touch screen in the classroom does not work well as I expect, I'm just gonna log in the Webex meeting with my touchpad here, so we'll have a better presentation of my notes. Grab the meeting information here. And so online students, can you guys see the OneNote?
Yeah, I can see it.
Or so this. So that is the blast load. That is the blast load. So as you can see here, showing the video, the blast load is a function of the distance. Right? We know that blast load should be a function of the so when you do design, and you will usually can have the given blast size function of equivalent TNT tonnage, right? TNT tonnage location. And so when you do design, for example, the owner of the oil plant needs to give you the distance from the potential explosion. So you will have a side view of the oil plants here, so that you can have a, you can refer to the ASC7, not ASC, the ASC blast load to calculate the blast load there. And typically, we also use that node as a deterministic node. Control block is also a deterministic. And when I was working in the industry, I happened to have a project, not oil and gas industry, but for the gold mining industry. The Armenia issue, so that's a gold mine. It hired us to design some buildings on their side. We had to consider some blast load, and Armenia they did not have any blast load specifications, so they hired us to use the ASC blast load specifications there. So that was some very interesting experience for me. So that was my first time to consider blast load. It is so different there. So when you consider blast load, you have to consider the high plasticity of materials, especially if you use metal materials such as steel or aluminum. You better consider the high plasticity of it, so that you can reduce the cost a lot. When you design the buildings, typically you don't want to design a bunker. You still want to make sure that the building is okay on the design glass look that occurs at the very high possibility there. So that's the glass look. And last time we also talked about the seismic load. So for seismic load is induced by the release of energy from aircraft atomic forces. Seismic load is due to release of energy. There are a lot of information between different parts of the Earth. If there are some fractures there, and the energy to be released, so that will induce the ground motion of the Earth. And that is the most severe load. Please. Earthquake load can be very destructive, especially if the building operators are not well detailed. So before 1970s in California, most of the buildings are not well detailed. So especially in the 1984 Los Angeles earthquake, bridge and collapse. So that's why nowadays in California, if you want to be a licensed professional engineer, you have to take an exam called the seismic design. You want to be a professional civil engineer, regardless whether you do geotechnic engineering or transportation engineering, you have to take seismic design exam. That's the policy in California. So earthquake motion is very complex. Earthquake motion is also very complex. So why? Because, for example, if we have a building here, so under earthquakes, typically you will have the motions in two translational. So you will have motion in two translational directions, or you will have translational in two perpendicular directions. Sometimes you also have the vertical motion. And sometimes you may have some torsional motion. You may have some torsional motion. So that means that the forces are moments in the actual building can be in any direction, So that means analysis for structures under earthquakes can be very complex. Yeah. So that's the. But how about the seismic load? Seismic load. So if we talk about the seismic load, in the engineering world, if you have already used the ASHTO or AS37 to do any seismic design, you know that the engineers, even there are very complex buildings and earthquakes, the engineers simplify that seismic load to ground accelerations. Engineering community. Acceleration. It's such as example. Is ground is also a function of the time. You have the x-axis t, the time, and the y-axis, that's the ground acceleration. It's very complex for us. Typically, at the beginning of the earthquake, the acceleration is very small, and then this is a typical earthquake wave. It will reach its peak acceleration and it will also decrease to zero at the end of the acceleration here. So, and typically we have the entire time here of an earthquake, when we call that is the duration of an earthquake. And that's the duration of an earthquake. And typically the duration of the earthquake is about, we have some very short earthquakes, maybe 5 seconds. And we may have some a little bit longer earthquakes. It's about maybe 50 seconds. 50 seconds. The earthquake occurs in a very short time, very short. And the last time, I think everybody had an opportunity to see the building on the earthquake. I'm not gonna play a video for that. So far we have talked about blast load and the seismic load, and as you can see here, both of them, the load is the function of time. The response of the structure under those type of load is much more complex than structure under static load. later on, let's talk about the live load. Live load. So when we talk about live load, so for bridges, we have the vehicle traffic, and we also have the people walking. So last time we watched a video of the vibration of a London Millennium Bridge. And then we also have the beauty. Machinery. So, for example, if you have a AC on top of the roof, when you design the roof permit for that building, you may also have to consider the vibration of the AC or ventilation system so that you can mitigate those type of vibrations. So now let me show you videos. So about the night load. So this is a very interesting.
it's still good. It only is 10 minutes long.
Yeah, so very similar, very similar, hazard to the bridge. For the bridge, okay, all right.
Yeah, I hope those people had insurance on their like rental trucks.
Very interesting. And so that means when you design this type of bridge, I would say the possibility for this bridge to have that kind of impact is very high. But for a typical bridge, if you have a required clearance for that's a straight road, I believe. Possibility that you would have the vehicular impact on the bridge will be very low, but when you do design, you still want to consider it. And that's definitely a dynamic law. And imagine if that bridge is on across a river, especially for a river with some ship traffic there. Want to consider the ship collision on the piers of the bridge. All of this impact of the dynamic load is a function of the load itself, as well as a function of the dynamic properties of the bridge itself.
I feel like 11 feet 8 inches isn't tall enough.
Yeah, that's probably enough. Another is about flow vibration.
Hi, my name is Julia Graham. I'm an engineer with RWVI's Vibration and Damping Group. I work on the prediction and mitigation of vibration in many different scenarios. Some examples are the vibration of tall buildings in the wind, the vibration of foundations supporting sensitive equipment, and the vibration of structural floors. Floor vibrations can become problematic if the motions are large enough that they cause annoyance or, in extreme cases, even panic. Recently, we worked on a project where such large-scale vibrations were a concern. This project involved a ballroom in a resort facility, and the unsupported area of the ballroom is more than 25,000 square feet, and the ballroom could have as many as 2,300 people in it at any time. So floor vibrations can become excessive when the natural frequency of the floor lines up with the frequency of excitation. This is a resonant response. In long-span ballrooms, we have a couple things working against us. First, the floor is very flexible, so that means that the natural frequencies are likely to line up with the frequencies of people dancing. And then we also have music playing, so that means that people are likely to dance or bob in time with the music. In this scenario, we have potential for many people to all be moving at frequencies that cause the floor to resonate. To predict the vibration response of the floor, we needed to construct a model that accurately represents the dynamic interaction between the crowd and the structure. When the mass of the crowd is significant compared to the mass of the structure, as is often the case in ballrooms and stadium grandstands, it is necessary to consider the dynamic interaction between these two systems. The crowd adds significant mass and damping to the system, which effectively modifies the dynamic properties of the system. If the dynamic interaction between the crowd and structure is not considered, as is the case in more simplistic models, then it's likely that higher than accurate accelerations will be predicted in the floor. We used a finite element method model to predict the dynamic properties of the floor, and then we worked with the architect and owner to develop an accurate representation of the people within the ballroom. We needed to consider not only the number of people, but also their locations and frequencies of damping and the percentage of people dancing versus standing or sitting still. We used these expected people layouts both to determine the loading scenarios for the floor and also to determine the dynamic properties of the crowd. We then used dynamic principles to combine the dynamic properties of the floor and the dynamic properties of the crowd to create a crowd structure model to which the dynamic loads of the crowd were applied. Our analysis showed that under certain loading scenarios, excessive floor motions were likely. To mitigate this response, we recommended tuned mass dampers, or TMDs. We worked closely with the structural engineer to determine the preferred TMD masses and locations, and then we constructed a model which represented the crowd structure TMD system. And this model actually incorporates 4 separate dynamic systems: the floor structure, the TMDs, the dancers, and the passive crowd. And we were able to use this model to show how the TMDs could effectively mitigate the floor's response.
Dancing versus.
So, as you can see here, when you design a building, mitigate the vibration due to the occupants' activities such as dancing, some walking, or sometimes running. And you have to consider the natural frequency of the floor system. Actually, AIC, American Institute for Steel Construction, they published several guidelines on how to consider the vibration of steel frame floors there. So when you design steel buildings, you do need to refer to these guidelines to make sure the vibration of the floor system can be well controlled, so that some people will not have a heart attack. And it's very uncomfortable. Sometimes when I work from this side of the campus to the residential side, through the pedestrian train over the Park River, I feel a little bit uncomfortable sometimes. Probably, yeah. Yeah, I was actually before the pandemic, I was thinking working with some students to for a project to monitor the vibration of that bridge, and they gave some recommendations to the universities, such as installation of some dampers or adding any mat to that bridge, so that we can reduce the vibration of that bridge. So it never started, unfortunately. Okay, so as you can see here, the real world, a lot of I would say, if you would like to have a structure safe for blast, vehicle impact, seismic, wind, you have to consider the dynamic properties, and you have to apply the knowledge of structural dynamics to make sure your design is good enough and meets the requirements by both of the building codes or bridge codes. And also, besides the safety, you also want to make sure the serviceability of your structures, such as the ballroom. You want to make sure when people use your ballroom or use the pedestrian bridge, or even a lobby of our building, you don't want to have most people have a heart attack due to the uncomfort over there. So structural dynamics is a very powerful tool for you to make sure to ensure the safety as well as the serviceability of your structures. So that's the introduction of the structural dynamics. And today we also got go over the general approach on how we can do analysis on a structural system over here. That's about that's my security. So that means that we need to know how to do the structure dynamic analysis of structures. So the first step, when you where you start the analysis, you want to have a way to express the dynamic load. So that and the dynamic load we usually call that expectation. Here, and then it's excitation. Excitation is a input to the structure. And output of our analysis is a response of the structure. And we typically, in most cases, we would like to start from the easy and easiest case. So we usually can model in order to simplify the process. We usually have a structural model as a discrete. What does this mean? That means, for example, so in reality, all the building materials, they are continuous materials, and including the elasticity and the mass distribution, all of them are continuous. But in most cases, we should be able to model them as a discrete parameter system there, so that we can have either, in that case, they are easy to formulate. And they are good to approximate the they are very, so in most cases, their response is very close to the distributed system. So for example, let's talk about the single degree. Firstly over here. Such as in this case, if we have a water tank, so that water tank is supported by a column, single column here. So if we consider some dynamic load, for example, we have a wind blower. So that if the wind induces some pressure on the on one side of the water tank, so this structure will have some displacement. So this structure will be displaced. So basically, we can have a displacement. So we use the letter U to represent the displacement here. Displacement. And we know that So per structural analysis, we know the displacement is a function of the height of the column as well as the lateral rigidity of the column. We need to know the height of the column, and we also need to know the rigidity, lateral rigidity of that column. So E times moment inertial. Okay, structural analysis. If we have a force here, we should be able to calculate the displacement if we are given the length and the height of the column as well as the EI of the column. Any questions here? So, as you can see here, the basis of the structural dynamic analysis here is very similar to the static analysis here. So we are interested in the relationship between the force and displacement here, displacement. So that means we can simplify this to a dynamic model here. So we have a mass on top here, and we have a column here. And a column here. So we should be able to find out the relationship between the force and the displacement if we have a displacement here. We have the force. Yes. So we should be able to have the express the force is equal to K times U, P times U. So where the K is the stiffness of that column, the K is the stiffness of that column. So based on the structural analysis, if we have a cantilever column here, what is the K value? So what's the relationship between K and EI and L? Equal to that's equal to 3 times EI per L cubic. This is structural analysis. Structural analysis. That means if you put a unit, if you put a unit force here, you should be able to calculate the displacement there, that you can get to the stiffness. That's the actually so far here. We still have a static model here, and so all of them are constant number with time. But we can easily change that static model to a dynamic model. And the most common dynamic model is called the mass free system. Be transferred to a dynamic. So this is so because we know that the stiffness of that column does not change with time. So it's a constant number. So we still have the constant of K. And the mass of that water tank, if we assume that the water tank is either full or empty there, so the mass is not changing, either. Is not changing either. So all of the K and M, they are constant number with time. So the only parameter in this system changing with time is the force. So we can easily incorporate the force as a function of time. So instead of having a constant force here, we have a force vary with time. And how about the displacement? Similarly, for the displacement, varies with time too, because if the force varies with time, the displacement varies. So that we can easily convert a static model to a dynamic model. And the dynamic model, that's the start of the dynamic analysis. So this is called and the spring system here. That's in the spring system here. So in order to do structure analysis, you need to come up with the mass spring system for any structure. That means you need to figure out what is the mass in the thickness of the spring, or such as the location of the spring as well as the orientation. So that's the start of the dynamic analysis. So now let's have a short break and resume the class around 8:45. Any questions from students online? Okay. No questions. Let's meet. Let's talk about that after the break.
Actually, I have a quick question. Do you hear me? Professor, can you hear me?
He's in Tennessee.
Okay, everyone. Parties.
Professor, can you hear me?
Go back to work. So, online students, if you guys hear me, so Michelle, I saw your microphones on, but do you have any questions?
Can you hear me?
Online students, can you guys hear me?
Can you hear
Us? Yep.
I cannot hear you. Interesting.
Okay. No, can you hear me? Can you hear me now?
Yeah, it's can you guys hear me?
Professor, can you hear me?
I cannot hear you. Interesting. Maybe